Hello, everyone. Today I want to share a paper from Google Research titled Titans, Learning to Memorize at Test Time. This paper introduces a new neural long-term memory module, which allows AI models to learn to memorize during testing, and can handle context sequences exceeding 2 million, 2M, in length. An important innovation of this paper lies in its proposal of a completely new memory architecture design approach. Although traditional transformer models can accurately model dependencies between tokens, they have significant computational bottlenecks in the self-attention mechanism. Each token needs to interact with all other tokens in the sequence for computation. This results in a computational complexity that is the square of the sequence length n superscript 2. For example, for a sequence of 10,000 tokens, 100 million interactions between tokens need to be calculated. This represents a huge overhead in terms of computational resources and memory usage. To address this issue, linear transformers simplify the attention computation to linear complexity O(n), enabling the model to handle longer sequences. However, this optimization comes at a cost. Linear transformers typically need to compress sequence information into fixed-dimensional vectors. And this compression inevitably loses some fine-grained contextual information, limiting the model's ability to model long-range dependencies and express precise relationships. The authors of the paper, from the perspective of cognitive science, argue that an effective learning paradigm should resemble the human brain, requiring the inclusion of multiple independent yet interconnected memory systems. Based on this idea, they designed the Titans architecture, which consists of three core components. First is the core module, core, which is like the working memory of the human brain, responsible for processing the current flow of information. This module uses an attention mechanism with a limited window size, allowing it to efficiently process immediate input data. Next is the long-term memory module, similar to the long-term memory system of the human brain. This neural long-term memory module is specifically responsible for storing and retrieving historical information, enabling the model to recall important content processed previously when needed. Finally, there is the persistent memory module, which is a set of learnable parameters that are independent of specific input data. It is like the knowledge structure formed by humans through long-term learning, used to store and encode general knowledge related to tasks. In terms of specific implementation, the paper proposes three ways to integrate memory into the model architecture, each with its unique advantages. The first approach is to use memory as context. This method directly concatenates the memory content as an additional input sequence with the current input. It is similar to prompt learning. The advantage of this approach is its simplicity and directness, as the model can naturally access the memory content through the attention mechanism. However, the drawback is that it increases the sequence length, thereby increasing computational overhead. The second approach is to use memory as a gating mechanism. In this method, the memory module generates a set of control signals to dynamically regulate the flow of information in the main network. This is similar to the gating mechanism in LSTM, but its scope is extended to the entire network. This approach allows the model to more flexibly decide when to use memory information and when to rely on current input, thereby improving the model's adaptability while maintaining computational efficiency. The third approach is to treat memory as an independent network layer. This method inserts specialized memory processing layers between standard transformer layers. Each memory layer can perform specific memory read and write operations. This design allows the model to process memory information at different levels of abstraction, achieving finer-grained memory control, but also increasing the complexity of the model. Experiments show that each of these three integration methods has its own strengths and weaknesses. The context method performs well on simple tasks. The gate method has an advantage in tasks requiring dynamic decision-making, while the layer method performs better on complex long-range dependency tasks. The authors of the paper recommend choosing the appropriate integration method based on specific task requirements, or combining multiple methods. In actual evaluations, the Titans architecture demonstrated comprehensive performance advantages. It outperformed transformer models with the same context window in language modeling tasks, showed strong reasoning capabilities in common-sense reasoning tasks, and was able to handle ultra-long sequences exceeding 2 million tokens. Additionally, The architecture also demonstrated good adaptability and competitiveness in fields such as time series prediction and DNA modeling. Of course, the Titan's architecture also has some limitations. The deep memory module brings additional computational overhead compared to highly optimized models like Mamba 2. The training throughput is slightly lower, and in some simple tasks. The complex memory architecture may seem somewhat over-engineered. Overall, this is a very interesting attempt. It does not simply stack more layers or increase the number of parameters, but rather rethinks the memory mechanism of AI models from the perspective of cognitive science. This approach may bring some inspiration to future model architecture design. That's all for the main content of this video. That if you're interested in this topic, feel free to leave a comment in the discussion section. Don't forget to like and subscribe, and we'll see you in the next video.